Brace yourself, because the equation used for these simple rectangular shape factors is probably the biggest, most disgusting equation you've seen in your entire college engineering career. And you're in a heat transfer class, so that's really saying something. But yeah, here you go on the screen. It's just rectangles, and yet it's this big, gigantic thing. So fortunately, instead of having to type a million numbers into your calculator, your textbook almost certainly has some figures that you can use, where just by looking up a couple of the dimensions of your rectangles, you can just use this figure to find an answer that'll be close enough. Now, that still doesn't mean that these problems are going to be easy, because radiation shape factors are spatial reasoning problems much more than math problems. You're going to have to use some creativity and kind of logical thinking to figure out how to get the exact shape factor you need when the table and the figures only give you different ones. So first, a super quick mini lecture just to explain what view factor even is, and then we'll get into the 3 example problems. There's really 4 different names for this thing, by the way. Radiation shape factor, radiation view factor, radiation configuration factor, radiation angle factor. So your textbook might use any of them, but they're all the same thing: shape factor, view factor, configuration factor, angle factor. What they all amount to is field of view. You have one surface that is emitting radiation, and what you want to find out is what percent of that radiation that's being emitted from the surface is hitting some other surface, right? If my desk is emitting radiation and I want to find out how much is going to be hitting my body, I want to know the view factor, because some of the radiation is going that way, some of it's going off that way, right? So a lot of it's going to miss me. I want to know what percent of it will actually hit me. That is the shape factor, view factor, configuration factor, angle factor. I'm just going to call it shape factor, or maybe view factor. I'll switch back and forth. So your final answer should always be between 0 and 1, because it's a percentage. And generally speaking, the closer together 2 surfaces are, the larger the percentage will be. And also, the more facing they are. That is, if you have surfaces over here, in order to get from this horizontal over to here, it has to take a real extreme angle, whereas most of the radiation will kind of come straight out. So I am going to make an assumption for this problem that we have diffuse surfaces, which simplifies it quite a lot. And I'm going to write down here 2 rules that are going to be used: reciprocity and superposition, which I'll explain more once we go through the example problem and you see how they're actually used. It'll make more sense what they mean then. All right, so your TA Serenity is going to nap through the whole thing, but your TA Indy he's a hardworking kitty, so he's going to be up here helping us out with problem part A. So from my figure in my textbook, this is a case 2 problem where you have 2 rectangular surfaces that are perpendicular to each other. But unfortunately, we can't look them up directly in the table because surface 1 is not touching surface 2. My table only works in the exact scenario where the 2 rectangular surfaces are touching each other. So I could find F2, 3, the 2 small, like half surfaces that are touching each other. I could also find F2, 4 to 1, 3, right? The big horizontal surface and the big vertical surface. Or I could find F2 to 1, 3, which is the small horizontal surface to the tall vertical surface. So your 2 rectangles are allowed to be different sizes, but they have to be touching. They have to share a common edge in order to use this table. And so far, I've only been talking about F2 as like the starting surface. And that's because, again, in my table, it's just drawn up as the bottom surface emitting up to the sides. So that's why I'm doing it this way. Later on, we'll be able to show you how you can flip the direction. So that's not a problem. So we'll start off by going ahead and looking up and using these tables just to get these first couple of shape factors. So for F2, 3, the 2 small surfaces, height, width, and length are 1, 1, and 4. And in order to look these up in the figure, I'm going to need H over L and W over L, which are both 0.25. So go to the table here, look up H over L is the horizontal axis, W over L is all of the swooping diagonal lines, I'm going to have to look kind of in between the 0.2 and the 0.4 to find 0.25, but so F23, 0.27. And we do the same thing for F2 to 13, where it's kind of the same, except now the height is twice as tall. We have an h of 2, so that leaves h over L of 0.5, which again, back here to the same table, I'm just kind of shifting over on the horizontal axis to the right now. And draw some straight lines. Looks like we've got F2 to 13 of 0.34. So that means about 34% of the radiation that leaves surface 2 is going to hit surface 13. So that kind of means about a third of the radiation is going to go kind of into the page and hit that surface. About a third of the radiation would probably then come like out of the page, kind of towards the viewer. And then the other third would go either off to the sides or straight up. So now the key to making our next set of progress on this problem is going to be using the superposition rule. So what superposition means is of all the radiation leaving surface 2, the amount that hits surface 13 is equal to the amount that hits surface 1 plus the amount that hits surface 3. That makes total sense. Some of it hits this surface, some of it hits this surface. You add those together and that's the amount that hits both surfaces. So this is really regular basic addition. And good news is that we already know two of these terms. We just found them. So if we plug in 0.34 minus 0.27 as we rearrange this, we get that F21 is 0.07. The amount of radiation that leaves surface 2 that hits surface 1 is 0.07. That's about 7% of the radiation. But for this problem, we were actually trying to find F12, right? We've solved backwards. So we want the radiation leaving surface 1 and hitting surface 2. So this is the other rule that you're going to need, the reciprocity rule or reciprocity principle. The area 1 times F12 is equal to area 2 times F21. So the relationship, when you want to reverse the direction of the radiation, they're not necessarily equal to each other. It's based on their areas. But in this case, since their areas are identical, then they are equal to each other. So F12 is also equal to 0.07. 7% of the radiation leaving surface 1 will hit surface 2. All right, part B is another case 2 problem, but this time neither surface 1 or 2 are at the corner. The approach is still going to be kind of the same. We're just going to figure out some shape factors that we can and use superposition and reciprocity to find the ones that we need by doing some subtraction and some reversing. So if you're really not sure where to start, just kind of guess something and just see where it takes you, which is kind of why students kind of hate these problems sometimes, because sometimes it's hard to predict where you need to go, but just try something. If you're not sure, try something and it'll probably help. It'll probably move you a little bit closer. So I'm going to start with just the largest possible, right? F24 to 13. So the entire bottom to the entire side. And the reason I might want this is that I'll be able to use superposition and I'll be able to divide this in half. So F from 24 to 13 is equal to 24 to 1 plus 24 to 3. And I'll be able to calculate two of those, right? 24 to 13, the whole side, that does share a corner, and also 24 to 3 also shares a corner. So let's go ahead and calculate those now. So for the big 24 to the big 13, height of 2, width of 2, length of 4, we've got h over L 0.5, w over L 0.5, and I can look this up in the figure and get an F value of 0.24. And then for the short height, right, height of 1, width of 2, length of 4, h over L is only 0.25, w over L 0.5. I now have F of 24 to 3 of 0.16 using the figure. And I can put these into my superposition equation and get from F24 to 1 is 0.08. And now eventually I want F12, so I don't want radiation going to point 1. I want radiation coming from point 1. So I'll use a reciprocity rule and flip this. So area 24 times F 24 to 1 is equal to area 1 F1 to 24. So I can flip it. I just have to account for the areas. So since 24 has area 8 and 1 has area of 4, F1 to 24 will be twice as much. It'll be 0.16. So the big area trying to hit the small area, only a really small percentage hit it, only 8%. But when we had the small area aiming at the big flat area, twice as much radiation hit it, right? Its field of view was twice as big, whereas the field of view up to the narrow point 1 was much narrower. Now that we've got two terms in the second half now, F1 to 24, we can split apart the 2 and the 4 by superposition. So F1 to 24 is equal to F12 plus F14. And F1 to 24 we just found, right? That was 0.16. And F1 to 4, this is actually the same thing that we found in part A. So I'm not going to resolve it here. I'm just going to use that same 0.07 that I found a couple minutes ago. Do a little bit of subtraction, and we get that F12 for this problem is 0.09. And now as I zoom out a minute, that's kind of interesting to compare that on part A, I got a shape factor of 0.07, and part B, a shape factor of 0.09. That means that more radiation emitting from 1 is going to hit the blue 0.2, even though it's further away. And so again, I said that field of view and shape factor, view factor is based on distance and angle. So the more like of a straight angle it is, the higher it will be, and the closer it is, the higher it will be. Well, in this case, we have one that's further away, but at a more gentle angle, versus one that's really close, but at a really sharp angle. And so it turns out that these end up almost canceling each other out. The numbers are pretty similar, but surprisingly, the one that's a little bit further away ends up being a little bit higher, 0.09. Again, mainly because it's more of a direct angle, it's less of an extreme angle. So one more problem left, part C. On my figure here, this is going to be a case 1 where we have two parallel rectangular surfaces. What's a little bit different about parallel surfaces than perpendicular is your parallel surfaces have to be exactly the same size to use this equation and to use this figure. With the perpendicular surfaces, it was okay if they were different sizes as long as they shared a common edge. But again, the parallel surfaces, they have to be the same size. So for this problem, I'm only really going to be able to solve two things by themselves, either like 1, 4 or 3, 2, right? The small ones that are on top of each other, or the combined 1, 3 to 2, 4, like the whole top to the whole bottom. I'm not going to be able to do like 1 to 2, 4, right? They have to be the same size. So after doing the past couple of problems, it seems like a good strategy for these is to start big and then use superposition to break your big shape into multiple smaller shapes. So I'm going to use that approach this time. Start big, use superposition to break it up into smaller pieces. So F24 to 1, 3. I've got A is 3, B is 2, C is 3. So A over C is 1, B over C 0.67. And looking at my table, this gets me an F24 to 31 of 0.15. And the reason I'm starting from the bottom, right, F24 pointed upwards, even though I want F1 at the end, is just because on my picture, F1, like in my tables, in the table is the bottom surface. So I'm just always starting with the bottom surface just to match what my tables show. And remember, at the end, whichever one I solve for, I can always flip them using reciprocity. So I just try to make it match your figure as best you can. All right, so now we jump into superposition, F24 to 1, 3. We're going to split 2, 4 to 1 and 2, 4 to 3. Now we know that f24 to 13 is 0.15, but we don't have any way to solve 24 to 1 or 24 to 3. I already said, yeah, we're not gonna be able to do that. However, you can tell based on symmetry that these two are gonna have to be equal to each other. The division between 1 and 3 is right directly in the middle above line or section 2,4. So half of the radiation that hits the whole surface is going to hit half, and the other half will hit the other half. So f24 to 1 is just going to be half of f24 to 13, so 0.075 just based on symmetry. So now since we've got 2,4 kind of as the emitting surface and 1 as the receiving surface, we can flip those by reciprocity so that I can break up the 2,4. So the superposition rule only lets me break up the second half, right? The destination. You cannot use superposition to break up the emitting surface. So superposition only breaks up the receiving surface. So using reciprocity, area 2,4 times f24 to 1 is equal to area 1 times f1 to 2,4. So this is just let me flip it by taking account that area 2,4 is twice as big as area 1, which means that f of 1 to 2,4 ends up being 0.15, right? Twice as big. And now this is kind of interesting that f1 to 2,4 is exactly equal to f24 to 3,1. And f24 to 3,1 and f31 to 2,4, right, just based on symmetry, those are going to be exactly the same. So what this means is that f1 to 2,4 is equal to f13 to 2,4. So if I add twice as much area to my emitting surface, I don't change the shape factor at all in this specific situation. And the reason that happens is, again, because of the symmetry. The same percentage of the radiation that goes from 1 to 2,4 is exactly the same as the percentage that goes from 3 to 2,4 because of symmetry. And so when you combine them, then the exact same percentage goes from the combined 1,3 to 2,4. So again, superposition only works for the destination, not the origin. It's possible that you can split up the origin, right? The emitting surface can get cut in half, and the shape factor doesn't change at all. I think that might be something you have to rewind and watch a couple of times and let it sink into your brain a little bit, just to let it sink in a little bit. But yes, f1 to 2,4 is exactly equal to f3 to 2,4, which is exactly equal to f13 to 2,4. All of those would be 0.15. They all would emit 15% of the radiation to the destination surface. Symmetry. All right, I'm rambling. Let's get back. We're almost done. Let's finish this up. So now that I have f1 to 2,4, I can use superposition to split up the 2,4. So f124 is equal to f12 plus f14. So f14, these two surfaces are directly above each other and the same size and shape. So I can look this up in my table. A of 3, B of 1, C of 3, A over C is 1, B over C 0.33. f14 is equal to 0.08. So put this in the subtraction, and my f12 value is 0.077%. All right, at least we didn't have to use those big gigantic equations, but if you're still not super confident with this topic and you want to watch another shape factor, view factor video, go ahead and watch the link up on the screen here for another view factor example problem.